Hello, my name is Varun Mishra, and today I'll be presenting our work on reproducibility in physiological stress detection. This work was done in collaboration with colleagues at Dartmouth, Northwestern, Washington University in St. Louis, and IBM Research. So what is stress? Simply put, stress is the brain's response to a challenging or demanding external stimuli. Let's do a quick review of the autonomic nervous system. When an individual is experiencing stress, the sympathetic nervous system contributes to what is called a fight or flight response. It signals the adrenal glands to release adrenaline and cortisol and results in a physiological impact like change in heart rate, breathing, and increase in sweat gland activity. On the other hand, once a person stops experiencing stress, the parasympathetic nervous system engages to help recover and reverses the effects of SNS. So occasional stress is actually good. In fact, most of you in the audience must have experienced that feeling stressed a day before a paper deadline pushes us to work harder. But continuously feeling such incidents of acute stress leads to a wear and tear on the body and could eventually lead to negative health outcomes. Due to the advances in sensing technologies, researchers have used sensors to measure these physiological changes to detect stress. In fact, one of the first works on using physiological signals to detect stress was done back in 2005, and people have been studying it since. So we are still trying to detect stress after 15 years. There are several challenges that exist, and one of the major challenges that our work focuses on is the lack of reproducibility and large-scale deployments. This is because of reliance on custom-made or expensive devices and sensors. Researchers often use their own custom hardware, which makes it inaccessible to conduct large-scale deployments. Further, in most prior works, the researchers built stress detection models using data collected from participants belonging to a particular demographic in a specific setting using a particular device. Such an approach makes it difficult to evaluate the efficacy of the models compared to a broader population or across devices. The model reproducibility is either assumed or left as future work. So in our work, we collected data from 4 different studies. The studies had different study protocols. 2 studies used the polar heart rate monitor and 2 used the Empatica E4. Across these 4 studies, we introduced some degree of heterogeneity with the different study protocols, populations, and devices. For more details about the individual studies and the study protocols, please refer to our paper. Then we started building stress detection models. We observed that the stress detection methods in prior works consider each time window that is used for classification as independent events. In doing so, they do not account for prior work and miss out on the temporal nature of stress. In our paper, we discussed different methods to account for prior stress and found that our methods consistently performed better than the approach in prior works across all 4 datasets. That is, our method was reproducible across studies. Due to time limitations, I will not be discussing the exact results from our methods. So if you are interested, we urge you to read the paper. But in this talk, I'll focus on our evaluations when we apply the models trained on data from one study to detect stress in another study. That is, to see the reproducibility of the models. So we'll evaluate the performance of the models trained using data from one study and tested on a different unseen dataset. The models output a probability of stress, which we then use with a threshold that was selected based on the training data to classify as stress or not stress. In the actual paper, we present the full comparison of each model with every dataset, but for this talk, let's visualize the performance of the models when evaluated with the S2 dataset. So we built models using S1, S3, and S4 datasets and evaluated them with the S2 dataset. For comparison, we have also included the cross-validation results of the S2 model. So we see that the F1 score from the cross-validation of S2 performs best. However, looking closely, we see that the models trained using the different datasets, there is a large variation between precision and recall. This suggests that the models might be working well, but it's the decision-making process, that is the eventual classification, that seems too selective. So to test this hypothesis, we decided to customize the classification threshold for each model based on what worked best for that testing dataset. So we immediately observed that the F1 scores were much better and consistent across all models. But in plotting the thresholds, we see that each model had a separate threshold that was used for testing on this particular test set, that is S2. This threshold, however, varies widely between model to model and seems to be dependent on both the training and the test data. Hence, at this point, it seems that the models trained on one dataset might not be enough or even very accurate to detect stress with participants from a different study. To get a better sense of what might be happening, let us look at the stress signal dynamics for a random participant from the S2 study. So we plotted out the likelihood of stress from each model for this participant. The dotted lines represent the optimized threshold for classification, and the shaded regions mark the baseline and the different stress-inducing tasks. It seems that the trends from the different models are similar, but the actual values differ quite a bit based on the training data. So this further strengthens our assumption that choosing a fixed threshold based on the training dataset might not work. But we cannot go away completely with the threshold either. If we want to provide an intervention, then some quantitative threshold is needed to determine when to deliver the intervention and to observe its effectiveness. So ideally, we would want to determine a custom threshold without any knowledge of the data in the test sets. One thing we know is that the likelihood ranges from 0 to 1. If the values are closer to 0, then the person is less likely to be stressed, and if it is closer to 1, then the person is more likely to be stressed. So we tried a clustering-based approach. We set 2 clusters with centers at 0 and 1 and fit the probabilities for each participant as we had new likelihoods were calculated. To visualize what's happening, we plot the results for S1 and S4 signal for the same participant. We observed that the assignment of labels of stressed and not stressed was quite consistent across this user. So we potentially have a way of determining a threshold of stress in an unsupervised way. We conducted thorough evaluations of our approach across all combinations of train and test datasets. And we found that our unsupervised approach consistently performs better than choosing a fixed threshold than a training set. In fact, in some cases, it even outperforms using an optimized threshold from the test set. This is great because now these models can actually be deployed in real world where there are no optimal thresholds. Our evaluations show that our methods and models are indeed reproducible, and as next steps, we are currently evaluating our models on additional datasets to test for potential generalizability. We are also planning to deploy these models in free living conditions and evaluate their effectiveness. Thank you for listening, and please feel free to reach out to us for more details.